Time to catch up with the naked scientist, Dr. Chris Smith. Chris, great to have you with us this morning.
Hello, Pippa. Good to be here.
Just a reminder to listeners, if you've got a question for the good doctor, please call us now on 021 446 0567 or drop a voice note to 072 567 1567. Chris, while we wait for the first calls to come in, can I ask the latest news on treating COVID-19? There was initially some hope around anti-malarial drugs that perhaps they might be of use, but I believe there was a piece published in the BMJ yesterday which has poured a bit of cold water on that theory.
When this was first mooted, it was from trials that was initiated in China, in Wuhan, and people just began to try drugs that they thought might have some kind of prospect of helping because they had nothing else to throw apart from supportive medical care at patients who had COVID-19. One of the things that they tried were these anti-malarial agents and their chemical relatives. This is chloroquine and hydroxychloroquine. And they also began to try some HIV drugs. There's a combo, lopinavir and ritonavir, which are given together. They're protease inhibitors, which block up HIV. But there's a similar sort of process going on with the way that coronaviruses grow, so people thought it would be worth a try. Some of those very small-scale trials on very small numbers of patients showed or appeared to show some possible benefits. So people thought we need to actually subject this to proper big-scale scrutiny, because it could be that if you do a small experiment that just by chance you find the result you want and actually there is no positive findings, it's just a chance. And that's now being done. People are doing much bigger studies, recruiting many more people. And this means that the study is much more powerful and has the capacity to detect cases that are responding or not responding and be more informative. So there isn't really any strong evidence that these agents like the chloroquine family are really making a big difference to the outcome in this disease. But what scientists are doing now are setting up proper high-powered trials to investigate other aspects of how the disease works. And we know that the disease falls into various phases. The first phase is because the virus grows in your respiratory tract, including in lung tissue, and it damages it. And when it damages it, it impairs its ability to work. But there's another follow-on phase after that, where the immune system moves in to get rid of the virus, but in the course of doing that, overreacts and does more damage to the respiratory tract, and that then further compromises a person's ability to breathe, and those are the COVID cases that often end up needing help in hospital. And so scientists are now asking, well, can we intervene early in this process and maybe damp down the immune system a bit? And this might help. So there are various trials in place now with various drugs which are able to manipulate the parts of the immune system that appear to be going most off kilter in the second immunological phase of the disease, and they're asking actively this question right now. So we should find out quite soon whether or not this is returning a benefit.
Thanks for that. And understandably, I think a lot of the questions today are likely to be around COVID-19, but just to emphasize, they don't have to be restricted to that topic. You're welcome to phone in on other queries as well. Having said that, we do go to Dr. Brian in Hermanus, who I believe is an immunologist who has a question or a comment. Brian, good morning.
Yeah, good morning. Good morning, Chris. I wondered if you'd care to comment on the new data, which is showing that very few people are being infected in countries such as France and Spain, as determined by antibody detection. In fact, less than 5% in countries where we've seen in excess of 27,000 deaths. And the implication being that the levels of herd immunity being achieved are falling far, far below expectation, and that which would be required to provide a decent level of herd immunity going forward.
Hi, Brian. This is correct, because we've not actually known for sure how many people in populations really have had the infection, because the tests we've had hitherto have been the have I got this right now type test. And the way that works is that we take a swab from the nose and throat. This will include, if it's there, material that's both the virus and cells infected with the virus. You extract the genetic information from that material and copy it millions of times and then read it. And if the virus genetic signature is in there, you can detect it. And so that tells you, have you got coronavirus infection right now? Now, obviously, those sorts of tests are limited in number. They are quite labour intensive to do, and therefore they take time to do. So all we've had is a moving snapshot of how many people have been catching this, and most of that testing is focused on people who are going into hospital, because you need to know when you admit someone to hospital, what is wrong with this person, where do I put them in the hospital, how am I going to manage their case. What we haven't been able to do is to ask, well, for every case that ends up in hospital, how many people out there in society are actually catching coronavirus and shrugging it off with few or no symptoms. We now can begin to do this because, as Brian alludes to, there is a new kind of test coming along now, the serology test. The idea of this is that you can look in the bloodstream for antibodies that a person makes when they fight off the infection. And because these antibodies are long-lived, once you have recovered from and eradicated from your body coronavirus, you are left with this immunological legacy, which are these antibodies which will circulate, and they will stay there for a long period of time, sometimes indefinitely. They can be detected, and they're there for a flag saying, I've had it. These sorts of assays are now becoming available. In the UK, an assay made by the company from Switzerland, Roche, has been approved by Public Health England, and it's also been given its European Union CE mark, which means it's regarded as a valid test, which is reliable, and that's now being wheeled out. And researchers are beginning to test samples of the general population, and what they're finding is that in London, about 10% of the population of the UK have had coronavirus. Outside London, it's about 5%. So across the country as a whole, it's hovering somewhere around 5%. Now, people had hoped that that number would be a lot higher. And obviously, the number will be refined as we test more people and find out how many people really do have antibodies. But it looks like that overall number is going to be quite low. But this will be useful because it will enable us to make much more accurate representation about what the real mortality rate of the infection is, and therefore what the risk is, and also identify where the hotspots are. If there are places in the country where everyone hasn't had it, then obviously that's a more vulnerable place for a flare-up than places where there's been a previous outbreak, everyone has antibodies and they are now immune.
What sort of percentage is deemed to be herd immunity? I've heard 60%. Is that sort of a standard figure?
It depends on what you're talking about. If you're talking about, say, the vaccination program for measles, delivered by MMR, the measles, mumps, rubella vaccine, then you need to be hitting 95% of the population, because we know that not everyone responds properly to the vaccine. Some people don't, some people fail to turn up for the second dose, etc. And so if you hit 95% of the population, you get immunity in north of 80% of the population, and this, we know, can suppress the spread of fairly aggressively spreading viruses like measles. And measles is really, really infectious. This new coronavirus is really, really infectious. We think that once we get to levels of between 60 and 70% of the population being immune, it will struggle to gain traction in a population. It won't be able to spread in the same way. So we'd certainly be looking for high noughts, so 60 to 70% of the population being immune to it, in order to retard its ability to spread. And obviously the numbers we're seeing at the moment are nowhere near that. So we've got no background level of immunity in the population of countries like the UK, which are obviously further along the curve of all this than South Africa is. And therefore we can't rely on the fact that were we to just ease all the lockdown restrictions, it wouldn't just come flying back with a vengeance and we'd have very big numbers very quickly again.
Thank you. Now, while we're talking about the antibodies, Jean in Cormacky had a question about that. Jean, good morning.
Morning, Pippa. Hi, Dr. Chris. Mine is obviously also an antibody-related question. What I would like to know is if you get a mild case of coronavirus versus a severe case that someone sits for 6 or 7 weeks with, do you develop different levels of antibodies, or is there a chance that a mild case won't develop any antibodies at all?
We don't know, and this is a brilliant question, and one that's actively being probed, because at the moment we don't know the people that have had a mild or no symptoms infection, because we haven't been able to detect them, because the way we've been detecting people is by asking, do you have these symptoms? And when people then turn up to hospital very ill, we test them, because we haven't just been screening the entire population, because that's not trivial to do. That it's not a criticism, it's just a fact that it's very, very difficult to do this at the sort of scale that we would need to do it. So now people are beginning to ask these sorts of questions. They are going and following up people, and there is a significant proportion of people who don't have any symptoms when they catch this. In fact, this week, the colleagues I work with in Cambridge at Cambridge University have published a paper in the journal eLife where they've where they've looked at a very similar question to this, which is they screened more than 1,000 healthcare workers in the hospital I work at, and that included going to these people and asking, have you had any symptoms? And of those people that said they had no symptoms whatsoever, about 3% of them at that moment in time were infected with coronavirus. On further probing, about half of the people said, well, I did have some vague symptoms, but I just dismissed them. I thought they were too trivial to not come to work, so I came to work. And so you can see there's a very healthy contingent of people who are walking around with coronavirus infection, potentially able to infect others, including their family members, other members of staff, and possibly patients in a hospital. And they don't think they're ill at all.
Thank you. And of course, the gene was Jean. My apologies for the mispronunciation there, but thanks for a very interesting question. Right, let's do one more about coronavirus before we move on to something very different with Andre. Dee is asking if you can please just explain a little bit more about the term viral load and in what circumstances one might get less viral load versus more.
Hello, Dee. The answer to this, the word viral load means different things under different circumstances. But normally when we're talking about the viral load, we're talking about, say, taking a sample from the bloodstream for, say, HIV or CMV, cytomegalovirus, and we would take that very standard blood sample and then count how many copies of the virus genetic information are in there, because each virus particle has got a copy of its genetic information in it, or if it's HIV, it's got 2 copies in each particle. And so if you count up how many copies of the genetic information are there, it gives you a marker for how much virus is in that person. And usually the more virus you have, the less well controlled your infection is, and therefore the more infectious you are, and the likelihood that you're going to become iller is higher. So it's a useful way of tracking whether a person is getting worse or getting better, and whether they're responding to infection. It means something slightly different in the case of the coronavirus infections that we're seeing, because people are using it to refer to how much virus is on a person's nose and throat and possibly lung tissue. And that's a slightly flawed measure, because unlike taking 1 milliliter of blood, that's a standardized sample, and counting all the virus in there, when we test for coronavirus, we're swabbing the nose and throat, which is not a standard sample. How is that standard? It's because we might be collecting more sample from one person and less from the next person. So very difficult to compare. So it's really only directional in terms of it gives us an idea as to whether someone is heavily infected or less heavily infected, because when we do the test on it, we can see how much virus is in the sample we collected. So we can roughly estimate, well, this person's very heavily infected, this other person is not very heavily infected. We don't actually know how that relates at the moment to how severe a person's infection is. The other point that people are making is when I cough and sneeze over somebody, if I've got it and I deposit a very big input to the person who I cough onto, some people are using that as viral load when they're saying you're exposed to a high viral load and that means you're more likely to catch it. It seems likely that that's the case, but we again don't know at the moment because we've not done the experiment where we've measured a person's viral load, as in a swab from their nose and throat, and then looked at how many people they transmitted it to. But those sorts of experiments and measurements are now being made, so we should get a bit more information on this before too long.
Thanks so much, and thank you, Dee, for the question. We're taking your calls on 021 446 0567 for the Naked Scientist, Dr. Chris Smith. Let's move away from COVID-19 for a while. Andre and Fish Hoek, you've got a question about water and the earth, I believe. Good morning.
Hi, Pippa. Hi, Dr. Chris. The question comes from the notion that, global warming, that a hotter world is a wetter world. And I was wondering whether our planet is a closed system in terms of the amount of water that we have. So at any given time over history, would there be the same amount of water either in glaciers, lakes, rivers, clouds, and so on, and that's then just moving around, obviously ignoring industrial processes?
The answer is that most of the water we have on Earth came here when the planet was quite young, and it arrived in the form of, initially we thought, watery comets, because comets are dirty ice balls, but subsequent analysis of the composition of the water that you find in comets compared with the composition of water that you find on asteroids suggests that actually it was asteroid impacts to the early Earth that brought a lot of the planet's water. So the water we have comes from several sources. One is that some of the material that made the Earth about 4.57 billion years ago had some water in it, but then the Earth was topped up by the arrival of comets and chiefly asteroids in the time since then. So the water we've got around us has been here a long time. It's actually not really changing appreciably now, but various processes do remove water from the chemistry of the Earth, but then they also make water. And so the Earth is effectively a closed system with the atoms that are in the water effectively being recycled. Because if you think about this, when you make some sugar in a plant leaf, so sunlight shines on a plant leaf, it grabs some carbon dioxide out of the air, mixes it with some water that's come up from the roots, you make a molecule of glucose, C6H12O6. You then eat the plant, and C6H12O6, a molecule of glucose, gets burnt in your cells with six molecules of oxygen, 6O2, and it goes back to, you've guessed it, 6 molecules of carbon dioxide, 6 CO2, plus water. You get 6 molecules of water as well. And so as a result, the water is there, but it's just in different chemical forms. But with global warming and et cetera, you might move where the water is in the Earth cycle. There might be more water in the atmosphere, for example, because of evaporation and so on, and redistribution around the planet. But we're not appreciably changing the amount of water in any given place on Earth.
Thank you so much, Andre, for an interesting question. Let's go to one that's come in on voice note.
Good morning, Dr. Chris. Could you please explain to me what water retention tablets do to the body? Thank you.
I think what's being referred to here, and thank you for this question, is the use of things like diuretics. And diuretics are drugs which cause the body to lose water. And they come in different classes and they have different ways of working, but the chief outcome is that they cause diuresis, which is that the kidney loses water, throws more water away as urine, meaning that the total amount of water in the body goes down. There's a number of reasons why you might use them. Sometimes if people have heart failure and they have absorbed too much salt and therefore water as well, they end up with too much water in the body. This overwhelms the blood vessels and the water can redistribute into the peripheral tissues. So you get swollen legs and things like this. And this can happen because of heart failure. If you take a water tablet, a diuretic, you lose some of this excess water and the water moves back out of the tissues into the blood vessels, out through the kidney, out into urine, and then the water's lost in the body, so the swelling goes down. So they can be used for those sorts of purposes. Also, just to get blood pressure down. There are certain classes of antihypertensive which actually are diuretics. And the way that works, again, is that if you reduce the amount of water that's in the blood vessel space, then you actually reduce the pressure, the circulating blood pressure. So they all have a common outcome, which is loss of water, but they do it in slightly different ways.
Thank you so much. Another voice note, quite an interesting one, this, about cooking.
Hi, Vic Marina de Gama. Quick cooking and scientific question. Why do stone fruits like apricot and plums, who are often quite sweet to start with, become sour when cooked down, and a lot of sugar needs to be added to it? Thanks.
I don't know the precise answer to that one. You've caught me out on that one. I'll have to go and have a think about it. One of the reasons is that when you cook these things down, what you do is you cause subsequent onward chemical reactions in the cooking process, and some of those chemical reactions will be caramelization reactions with the sugars. And despite the name, not all the caramelization products are sweet tasting. They can be more bitter tasting, so that's one reason. The other is that you also bust open the tissue. When you cook something, you break open all the cells and you therefore release the other contents and things that are in the tissues, which when you were to just bite into them and get the immediate sugar hit, you wouldn't necessarily taste those other chemicals so high in the mix. But when you stew something down, then you release all of the things that are in all of the cells in the materials in the fruit, and therefore you'll get a slightly different flavour spectrum. So I'll go and check this to make sure that my speculation isn't completely off kilter. So take this one with a pinch of salt, but not too much salt because it's bad for your blood pressure, until next week, and I'll confirm, but I would speculate those are why.
Thank you so much. A question in on Twitter from Victoria. Do we definitively know how memories are stored?
Sort of. There's lots of different types of memory. There's short-term memory, long-term memory. There's what we would call episodic memory, where you can ask me, do you remember that time we went to the beach? And I'll say yes. And then there's things like motor memory. Can I remember how to drive a car? So there are lots of different sorts of memories. But the general trend in storing information in the brain is that it's stored in the connections between nerve cells. There's something like 100 billion brain cells in the average human brain, and those cells are connected to each other at structures called synapses, which is where small projections from the nerve cells touch an adjacent cell, and the synapse, when the cell is active, squirts a nerve chemical onto the cell next door and changes its activity. It either makes it more or less excited. And by changing how many of those connections are made between which cells, you can use this to make circuits, which effectively are like logic circuits. They store information. And when we make memories, we change the density of connections between different groups of brain cells. And so we think that short-term memory is made in a structure in the brain called the hippocampus. And then as you translate that memory to longer-term storage, it's exported to other parts of the brain where you lay down these connections between nerve cells that then store it for the long term.
Thanks again, Victoria, for participating this morning. Interesting question. Right, while we're dealing with strange food-related questions, here's one from Roberta on WhatsApp. Wondering if you can please explain the function of the thin bone which runs parallel to a chicken drumstick.
This is very similar to if you look at, say, your wrist, or you look at your lower limb, you see that there's not one bone there in your arm or your lower leg, there are two. So in my wrist, for example, I have my ulna and my radius, and the ulna is the one that forms the hinge with my elbow and goes to my hand, and the radius runs along the top and then forms the main part of the wrist joint. Similarly, with the ankle, you've got your tibia, which is the big fat bone in the middle, and then on the outside edge is a thinner bone that goes down to the ankle, and that's your fibula. So yeah, it's not unusual to have a supporting bone in certain parts of the body, and the role that bone plays is to support a distal joint, give an anchorage point for muscles, and enable the limb to have more degrees of freedom in terms of its movement in a mechanically stable way. And I think the bone in the chicken, and I'm not a vet, so I'll ask a vet to check this later.
Sure.
But I'd say that's it's all about mechanical stability of the structure downstream.
Roberta, obviously very thoughtful about what he is eating. Thanks so much. Okay, I think we can squeeze in one more question by voice note. Let's take a listen.
Morning, Pippa and Chris. Chris, if one is asymptomatic, has it been proven that there is a time limit, an expiry time for your asymptomatic state to stop, if you know what I'm saying? Does one stay asymptomatic? Thank you. This is Roslyn.
Roslyn, I think what you're referring to is if you catch, say, coronavirus infection and you're asymptomatically infected, A, can you get it again? And B, how long do you remain potentially infectious for? Well, we don't know exactly how long people remain infectious for if they're asymptomatic, because obviously we don't know about them if they're asymptomatic at the moment, because we haven't tested very many people like this. But what seems to be the pattern is that you incubate this thing for an average of 5 days and up to 14 days. You become maximally infectious from the time just before the symptoms kick in, if any. So that would suggest, if you're being asymptomatic, that after about 5 days, you become maximally infectious. And we know that you remain infectious and capable of transmitting it for about 4 or 5 days after that. And then once you're beyond that time point, the immune response means that the amount of virus in you drops precipitously, and therefore your chances of passing on the infection to anyone else remains very low. And beyond that, you've got a strong immune response and antibodies, so you wouldn't catch it again. And therefore, we think, you're not going to have any kind of infection from the same type again, at least in the short term. And therefore, you'll remain effectively asymptomatic because you haven't got any infection after that.
Okay, let's finish with a very quick one from Noor on a different topic. Noor would like to know the following. When one switches the light off, there's a little dot left in the center of the vision, making us unable to see clearly in the dark. What causes that dot?
Well, the way your eye works, you've got in the centre of your vision is your macula, which is the most sensitive part with the highest acuity. It's the bit that you focus light onto when you want to read and see things very clearly, watch the TV or look at someone's face to recognise them. And when we do something that involves looking at something, we're focusing light on that part of the retina. When you have been looking at the light and then you turn the light off, the light that was falling on that part of the retina has temporarily bleached out or used up some of the chemicals that the retina uses to turn light waves into brain waves. And so for a little while, that area is a bit less sensitive and it appears as a brighter spot compared to the more sensitive other parts of your retina. And then as you get used to the light, you bring into play more of your rods, which are the more light-sensitive visual elements in the retina, and you also make more of the visual pigment so that you can actually detect more photons of stray photons of light in the darkness. And so your vision becomes a bit more acute, but it's never as good on that central spot at seeing dark in the dark as the more peripheral parts of the retina, which is why if you want to see something in the dark like a star, always look slightly off to the side, because the bits around your central vision are more sensitive than looking straight at it.
Really interesting answer. Thank you so much. So look slightly to the side to get the best possible view.
In the dark.
I have to ask.
In the dark, because
Yeah,
it's although
the
your
dark.
central vision is the most acute, it's the peripheral vision that's the most sensitive in the dark. It's more light sensitive, but it's got less acuity.
Thank you. And I have to ask, does eating carrots help with vision in the dark?
We think this was a myth that was put out during World War II. We've just celebrated VE Day, Victory in Europe Day, last week. We think this was a myth that was put out during the war to throw the Germans off the scent that the British had radar. And they were saying to everyone, our pilots are so good at spotting the enemy because they eat loads of carrots. In fact, it was because they built a huge network of radar stations around the coast. But carrots do contain beta-carotene, which is two vitamin A molecules, retinoic acid molecules stuck together, and as the name suggests, retinoic acid, you do use this to make important pigments and chemicals in the retina so you can see, but most people are not deficient in vitamin A except under very exceptional circumstances, so carrots don't actually really help you see in the dark.
Shh, don't tell your kids, anyone. No need to share that too widely. Dr. Chris Smith, always lovely having you on the show. Thank you
Thanks,
so much
Pippa.
for joining us.
Bye-bye.